Hello and welcome to the lecture on the interference of sound waves. Okay, so we're going to talk about two ways that sound waves can interfere with each other. And to understand the idea of interference, just refer to the general section on wave interference that I lectured on earlier, where I talked about the principle of wave superposition and how that can lead to destructive and constructive interference, because that's what we're talking about here today. So the two ways that waves can interfere are spatially, so these are two waves that overlap or coexist at the same point, or in time, which I guess you could say is temporally, right? So the idea there is we have time interference and space interference, or position interference. And it's simply that we hold one thing constant. So in the case of spatial interference, we hold the frequency constant, and we're only concerned with different distances from two sources of sound. And in the case of time interference, we actually vary the frequency and we hold the position constant. All right, so it's just focusing on different aspects. Now we'll talk a lot more about spatial interference in our next and final lecture on sound waves to conclude this chapter, but we won't talk anymore about beats. This is really the one time we're going to talk about the phenomenon of a beat. And by the way, a beat is just time interference. It's just two waves of different frequency. All right, so again, expect a lot more about spatial interference, specifically in regards to standing waves, where there are two waves that interfere with each other, one incident and one reflected, in the next lecture. But let's get on to this lecture. All right, so the first key term, spatial interference, let's elaborate on that. So it is interference of two waves of equal frequency, see here, that's what we're holding constant, at a particular location due to phase differences, which can be caused by differing distances or reflection. All right, and this interference is constant because as long as you stay at that same point and let the waves continue to pass over you, the interference does not vary. It is constant because constant refers to a time aspect. It is not time dependent. In other words, it's time independent or constant. Okay? All right, so the idea there is we're going to have different sources and a phase difference. And of course, we have some familiarity, if you remember, that what phase differences we should expect for wave cancellation and wave addition, and those would be things like half a wavelength or integer multiples of a full wavelength. Okay, so now on to the idea of a beat. Okay? Now, and these are the formulas we're going to look at for spatial interference. I'll get to those in just a minute. So first, the key term of a beat. Okay, so a beat is interference of two waves at a particular time and location, but you're holding the location constant, where the two waves have different frequencies. See? Before it was equal frequencies. And we could combine the two, but we don't, right? We'll always have separate problems between the two. So if there are different frequencies of two sounds, then you're going to be asked something about a beat. Okay? And thus the phase angle is non-constant. Sometimes the waves are in phase, sometimes the waves are out of phase. Because if you have two waves passing over an observer at a fixed point, then you think about that those two waves have different frequencies, then over time there's going to be moments where they are constructively interfering and then moments where they're destructively interfering. And that's going to create an amplitude that varies between 0 and maximum. And that variation in the amplitude is known as the beat frequency. It leads to beats. So beats are a frequency of the amplitude. So the frequency of the total amplitude. Now, in practicality, they just take a simple calculation down here. All right, so let's look at our equations. They are pretty straightforward. So for spatial interference, we look at a difference in the distance to the sources of the waves. So this delta D refers to the differing distance to two wave sources. We're only ever going to consider two wave sources, all right? And if that differing distance, what we might call the path length difference between the two wave sources, is equal to the wavelength of the wave sources multiplied by 1/2 plus n, then we get destructive interference. Okay? Because what we're saying there is we're saying that the path length difference is equal to some integer multiple of half wavelengths. All right? That's what this formula is telling us. And it doesn't matter if one is further away or one is closer, hence the plus or minus. But if there's that path length difference, that means that the waves will always arrive out of phase. We're always going to have one wave arrive as a trough and the other wave arrive as a crest, and they're going to cancel each other out. Okay, that's destructive interference due to a difference in the distance to the two wave sources. On the other hand, we could have the waves add up, and then we could have constructive interference where the path length difference is a multiple of their wavelength. And notice there's two waves, but there's only one wavelength. That's because spatial interference always involves waves of equal frequency, which also means equal wavelength. All right? Now for beats, since the frequencies are different, we have a formula that involves the two frequencies, and then the beat frequency, which is that amplitude frequency, that's the sound going from quiet to loud, quiet to loud. Well, that is equal to just the absolute value of the difference between the two frequencies. All right? So if you have two frequencies that are very close to each other, say two sounds, pure sound waves, maybe one is 300 hertz and the other is a 301 hertz, well then you'd have a beat once per second, which means you would hear a sound that sounded a lot like a pure 300 hertz sound, because the actual total frequency would just be the average of the two. But then the actual amplitude would vary. So it would be something like That's what a beat is. It's loud to soft and loud to soft because of the differing frequencies of two waves than being perceived by a microphone or the human ear. Okay? All right, so let's get on to some practice problems involving these topics of spatial or time interference of traveling waves. Okay, so example 1 is going to be one that involves spatial interference. So the temperature is 22 degrees Celsius. An observer stands directly in front of two speakers, one in front of the other. The two speakers are emitting the same 650 hertz sound. That's a good sign it's going to be a spatial interference type of problem. If one speaker is 20 centimeters behind the other, what minimum distance must it be moved, typo there, should we say it, in order for the person to hear no sound from either speaker? So what type of interference are we looking for? Yep, destructive interference. Okay, all right. Oh, and by the way, using these formulas, I got ahead of myself, but using these formulas, there's an n in here. This is just that idea of counting integers. So n can either be 0, 1, 2, 3, or any integer, okay? And the idea there is that, of course, you can get interference as long as you meet the criteria that the waves are out of phase. It doesn't matter if they're exactly half a wavelength out of phase, say for a destructive interference, or 1.5, or 2.5, or 3.5. It will all have the same effect. Hence, the formulas work for any integer. Okay. All right, so let's get back to a problem that involves that. So here are two speakers, two wave sources. They have an initial distance between them, which I call d naught, that is the 20 centimeters. Okay, there's going to be some observer over here that's going to be hearing the waves. Essentially what's going to happen is we want destructive interference. So we want it so that one wave will have completed half a wavelength between the distance of the two speakers and then be producing a trough, while the other speaker is simultaneously, due to its differing distance from the observer, creating the initial crest. Now this is assuming that the waves are initially created as sine waves, which is a fine assumption. We could have assumed they were created as cosine, but it wouldn't matter. But then the point is that once they arrive at the person, they're arriving exactly a half length out of phase, which means they're exactly canceling out. And the waves will continue to pass over the person, but they'll always cancel out because they'll always have the same out of phase nature. Okay? That's what we're looking to satisfy here. So we've calculated the temperature in Kelvin, 295, converting from the 20 degrees Celsius. Then we're going to calculate the velocity of sound at that particular temperature, which works out to be 344 meters per second. Then we're going to find the wavelength given the frequency and the velocity of sound at that temperature. And we get a wavelength of just over half a meter. Then we know for destructive interference, we want to have some integer multiple of a half wavelength. I'm going to look initially at the one that's just exactly 1/2 wavelength, and I get a value that is 0.265 meters. Now, if that had been nowhere near our separation distance of 20 centimeters, then I could have continued to have looked at the greater differences in path length that lead to destructive interference. But here it looks like 1/2 of a wavelength is going to be pretty close to our initial separation distance of 20 centimeters, so it's a great candidate for our minimum movement of one of the speakers. All right, so you can see that in order to get the speakers to create no sound perceived by a person some distance away from them, we need to have the distance between them indeed be exactly 1/2 a wavelength, which means we need to move the speakers 6.5 centimeters. We either need to move this one 6.5 centimeters to the front, or we need to move speaker 1 6.5 centimeters back. but we need to increase their separation distance from 20 centimeters to 26.5 centimeters. Okay? All right, so hopefully that looks good. Let's move on to the next example. All right, so this is another spatial interference problem. This one ends up being algebraically very complex, but it's a good illustration of how we can still solve it. So we have two loudspeakers, very much like in the previous problem. They're placed 3 meters apart, as shown, and they emit a 474 hertz pure tone sound. A microphone, shown here, is placed 3.2 meters, a distance from a point midway between the two speakers, like so, where an intensity maximum is recorded. Now, why would it be a maximum? Well, because D2 and D1 are equal to each other. You see that? Because we have a isosceles triangle, and therefore D2 and D1 are equal in length, which means if they have equal length paths, then they are arriving exactly in phase. Okay? All right? Which means they're constructively interfering, just to be clear. So then the question is, how far must the microphone be moved to the right, so this direction, all right, I guess that's the left, but point doesn't matter, in order to find the first intensity minimum. So now we want to get a case where we're going to have different path lengths from the two speakers so that the difference between the two is exactly equal to 1/2 of their wavelength. Okay? Because we want to have the minimum distance. Okay? It's the first intensity minimum. Because if we continue to move the speaker to either the left or the right, we continue to pass through regions where the path length differences are going to cause constructive interference and where they're going to cause destructive interference. All right, we'll just pass through one after the other, okay? Because this is a perfect situation. There's no reflected sound. This is just these two sounds. Nothing else exists in this system. If you really wanted to do this, you can. Some science museums do it. The key is to avoid any reflection of sound, because obviously you do this in a room, the speakers are going to produce sounds that bounce off the walls, and so now you have lots of sounds rather than just the two sources. So you must have a room where the walls are surrounded by a very good sound absorbing material, and then you can actually simulate this in the real world. Okay, so I showed the speaker indeed moving to the left, even though I said the right, okay? But again, it does not matter, okay? But we are going to be moving a lateral distance, and look at the new paths now. We have D2 prime, which is the distance from the new microphone location to speaker 2, and we have D1 prime, which is the distance from the new microphone location, right, so right here, to speaker 1, okay? Now, obviously, D1 prime is going to now be longer than D2 prime. They're no longer equal. See it? Okay? And L is still the distance that we're going to consider in order to make a couple of triangles, because we're going to consider two right triangles where they both have one side of the triangle L, one side D, 1 or 2 prime, and then that will allow us to, solve this problem algebraically. Okay? All right, so we need the new delta D, which is D1 prime minus D2 prime, to be equal to 1/2 the wavelength. And that's going to be the criteria for destructive interference. So that's the setup. No different than the last problem. It's just that now we have, a lot of right triangles to consider. Well, D2 prime is expressed this way in terms of our known variables. Because think what we know. We know L, that is our 3.2 meters. We know how far we're moving the speaker, or we're trying to solve for X. And we know and then we also know the value of 3 meters here. Okay, that's our D value. So you see that? All right, so just to be clear on what this 1/2 D minus X and this 1/2 D plus X is, okay? So if you look here, now I'm gonna show this side prominently, okay? That is the 1/2 D minus X. See, because again, D is 3 meters, right? And if I move it a distance of X, then that means that side of the right triangle is 1/2 D minus X. On the other hand, this right triangle here, okay, what's this length? That length is 1/2 D plus X. See it? Okay? And that means that by the Pythagorean theorem, the two hypotenuses that we're interested in, D2 prime and D1 prime, here they are, expressed in terms of all knowns except for one unknown, which is X. And that's what we're going to solve for. We're going to solve for X. Okay? So we're going to take these two expressions and plug them into our destructive interference criteria equation, like so. All right? See what I've done. All right? I've just rearranged it by putting D2 prime on the other side and then having my L over 2 over here. Okay? Actually, I put my D2 prime on this side and then I wrote that as the left-hand side. See? Okay? Because that D2 prime indeed is the shorter side, and now it's on the side with the lambda over 2. Okay, so as you can see, I've just rearranged the equation. Okay, now take a look at that equation. And remember what we're solving for. We're solving for x. That is a pretty big ask. Now, you could just plug this into a computer algebra system. You could solve it graphically as well. The whole point is that there's only one unknown variable here. Everything else are just constants or specified values, right? Okay, and by the way, we would find lambda by using the same the speed of sound calculation and the frequency, and then you can calculate lambda as in the previous example. I'm going to go ahead and run through the algebra just to show that it can be done. You can actually solve it by hand. So we're going to square both sides. Okay, so when we square both sides, we get this expression, which basically just looks like everything is getting worse. But the point of squaring algebraically worse, that is, the point of squaring both sides is to get rid of the square roots. But we see we didn't completely get rid of the square roots because when we squared this side, we ended up with a middle term that still had a square root. Well, what should we do? Square them again. All right. So first of all, I'm going to rearrange things, clean it up a little bit. All right. I've combined like terms, cancel out things that cancel, and then I'm going to square both sides again. And that actually is a common algebraic approach. All right. Because now we've gotten rid of the root completely. Okay. So now I'm going to factor and distribute, combine like terms, cancel out anything that can cancel. And finally, I've got this expression and a solution. I solved for x algebraically, right? We get a quite a big expression here. This actually is a pretty common phenomenon though, because this is going to apply to light interference as well. So I'm going to go ahead and put a circle around this because this is a nice derived equation. Okay, now for this particular problem, we'll just plug in our values, all right? So first of all, find the lambda, which ends up being the wavelength, that is, ends up being 72.2 centimeters, and that's based on a standard velocity of sound. I'm assuming 343 because the temperature was not specified. All right, divide by the frequency to get the wavelength. All right, divide the velocity by the frequency, of course. All right, and then we'll plug everything into our expression, which we got through our algebraic fancy footwork. And there are the numbers, and there is our answer. We have to move 43 centimeters to the side, either the left or the right, in order to find our first minimum, our first point of silence. Okay, so pretty cool problem, I hope. All right, let's look at a couple more. The next two problems are all going to be about, you guessed it, beats. All right, so this is interference in time. So first one, a guitar string produces 4 beats per second when sounded with a 350 hertz tuning fork, and 9 beats per second when sounded with a 355 hertz tuning fork. What is the vibrational frequency of the string? So the idea of beats and using a tuning fork is actually the way that people tune musical instruments. Certainly when you think about tuning a piano, it is done with very carefully engineered tuning forks of precisely known frequency. A key is struck on the piano, the tuning fork is struck simultaneously, and the piano tuner listens for that beat. Because if they can hear a beat, then they know there is a discrepancy in the purported frequency of that key and the actual frequency of the key. Thus, the key needs to be retuned, okay? And that's what we're doing here, but for a guitar. So the first thing, we use the first tuning fork and we consider the beat frequency of 4 hertz. Okay, well in that case, we're using our 350 hertz tuning fork and we get 4 hertz. So considering the absolute value definition of the beat frequency, that tells us that the frequency of the guitar could be either 354 hertz or 346 hertz. We're not sure. We just know that it's 4 hertz different from the tuning fork, okay? You see how that works? We're not sure what it is. It could either be 4 hertz greater, which would be the 354, or it could be 4 hertz less, which would be the 346. Hence the necessity of the second tuning fork. The one tuning fork doesn't tell you for sure, all right? It just tells you the difference. So then we use the second tuning fork, and then we consider that we're getting 9 hertz on our beat frequency, and our second tuning fork is 350. That means that the two possible values of the guitar string based on the results of the second 355 hertz tuning fork are either 364 hertz, because that would be 355 plus 9, or 346, which is 355 minus 9. Well, you guessed it, because I already circled it, that the only value that overlaps, that is consistent between the two tuning forks, is the 346. Thus, we know that the guitar string has a frequency of 346 hertz, which may require tuning. We don't know, okay? Or maybe it turns out that the guitar is perfectly in tune. All right. So that's the idea. You always need 2 tuning forks and measured beats while sounding that tuning fork in order to tune an instrument. Okay, all right. So let's move right on to the last example. This one is a beat problem, but the setup here is the Doppler effect. So it's basing information off the Doppler effect as well as reflection of sound, and then following up with asking a question about beats. So an ambulance sounding a siren of a frequency of 687 hertz is traveling towards a vertical reflecting wall with a speed of 15 meters per second. If the wall is moving in the same direction as the ambulance, but with a speed of only 5.5 meters per second, what is the beat frequency heard by the driver of the ambulance? So first of all, I'm going to assume a velocity of sound of 343 meters per second. Then we're going to acknowledge that this problem has 4 steps. Graciously, the 4 steps are very simple, but we got to make sure we don't miss any of them. Okay? So first of all, step 1, the ambulance is a source and the wall is an observer. That's going to give us the reflected frequency. And this involve using the Doppler effect formula. Okay? Then instantaneous reflection with no change in frequency. So when the sound bounces off the wall, it doesn't change its frequency. Okay? There's no effect on the frequency. Now there would be an effect on the actual spatial aspect of the wave, because there would be an inversion, because this is basically a fixed surface. So there would be an inverted wave, but there would be no change in the frequency. Okay? If you remember the law of reflection, the idea here, no change in frequency, just change in the phase angle. Okay? But the phase angle doesn't matter here. So then on the step 3, now the wall behaves as a source. All right, so the wall as the source and the ambulance as the observer. This is going to give the final frequency observed by the ambulance. Now, to be fair, there's 2 frequencies being observed by the ambulance. The original frequency within the ambulance, and now this new reflected, twice Doppler affected frequency. And then finally, we'll take the final frequency and the initial frequency of the ambulance to find the beat frequency. And there you'll simply take the absolute value of the difference between the 2 frequencies. All right, so step 1 looks like this. We use the Doppler effect formula, all right, to find the sound as basically perceived as the wall if the wall could perceive the sound. And that is 706 hertz. Where do we get that? Well, we get that because we have a source moving towards the wall, we have a wall moving away from the source, and here are respective velocities for the wall and the ambulance. Okay, so there we have an increase in the frequency from 687 to 706. Okay? And then step 2 doesn't require any calculation. So in calculation-wise, we can move on to step 3. And then we're going to take the 706 hertz as the source frequency from the wall, and then it's going to travel back to the ambulance. But now, relative to the wall, the ambulance is moving towards it, and the ambulance is the observer. So we have that up top with a positive because that's an observer moving towards. Meanwhile, the wall now is the source, and it's moving away, so we have a positive. So notice what that does. That now will increase the frequency a second time from 706 to 726 hertz. And this is quite interesting because if we were just to do the Doppler effect once, we would not get the right answer. We have to do it twice, all right? And review these steps for further understanding. Okay, so then finally, we can then just plug in these 2 frequencies into the beat frequency, or the beat formula for the actual frequency of the beat. And again, the frequency of the beat is the frequency of the amplitude. That's just loud to quiet, loud to quiet. All right, and so it's just the absolute value of the difference between 687 and 726, which is 39.2 hertz. That means that this particular sound is going from loud to quiet almost 40 times per second, which means you may not be able to perceive it. Because the thing about beat frequencies is the human ear won't perceive them if they're too fast. Because something goes loud, quiet, you can't really tell if it's doing that many times per second. Okay? All right, so there you have how to calculate the beat frequency given a problem that involves the Doppler effect. Okay, well, I hope this lecture on wave interference has been interesting and informative. And again, expect to employ these ideas in the next and final lecture for this chapter. Thank you so much for watching.